In this video I'm going to talk about the Ramsey's theorem for two colors. So we consider colorings of a complete graph in two colors, of colorings of edges. So let's first draw a picture. So let's say that we have a complete graph. So I will so this is a complete graph on 4 vertices. So we consider coloring of its edges in two colors. So let's say we have this color 1, 1, 2, 2, 1, something like this, and this let's say 2. So then basically what the theorem states is that so we look for cliques. So a clique is a subgraph that is a complete graph. So a clique on 3 vertices, for example, is this. So this is a clique on 3 vertices. So we look for cliques that are of the same color. So cliques of color 1, we look for. So let's write this. Then we'll state the full statement of the theorem. But first, let's write this. So we look for cliques of color 1. So where all edges in the clique are the same color, and this is color 1, or cliques of color 2. Of color 2. So for example, in this graph, we there is a clique of size 3 of color 2, right? So this one. So this one, this triangle, all 3 edges in it have color 2. But for color 1, there is no clique. So so we look for cliques where all edges are of the same color. And so now we denote, so now basically the theorem states that if we take the original graph large enough, so here we took the graph on 4 vertices, but like if we take the complete graph on n vertices, if n is large enough, so if n is large enough, then basically we can find these cliques. So this is the kind of general, imprecise for now statement, and the full formal statement is here. I wrote it here. So let's say this. So so for any x and y natural numbers, there exists a number r xy, r of xy, and we say that it's a minimum number such that for any coloring of edges of the complete graph on this number of vertices of r of xy, there exists either a clique of color 1, the clique where all vertices, all edges colored in color 1 on x vertices, or a clique of color 2 on y vertices. So basically r of xy is the minimum size of the original graph, of the complete graph, such that we can guarantee that there exists either a clique on x vertices of color 1 or a clique on y vertices of color 2. So, and this is a minimum number with such property, and the theorem states that this number exists. So basically the theorem states that r of xy is less than infinity. So r of xy exists at all. Like exists. That's the statement of the theory, or like another way to write it is that it's a finite number, that it's less than infinity. I'm not going to write it. Okay, so so let's consider the proof. So we're going to prove by induction. So we are going to prove it by induction on x plus y. So induction on x plus y. So the base case for the base case basically like it's like we consider when x is equal to 2 and or y is equal to 2, like or y is equal to 2. So then what we have is like, so basically when we need to find r of 2y and r of x2. So why this holds? So basically we notice that in any graph, so because clique of size 2 so a clique of size 2 is just an edge. All right, so when we have a complete graph, so the condition that we have a clique of size 2 of color 1, it means that we have an edge of color 1. So clique size 2, it's the same as an edge. So the condition to have a clique of size 2 of color 1, it means that we have an edge of color 1. So if we have an edge of color 1, then this is defined. So the only case when this is not defined, the only remaining case is when we don't have an edge of color 1. It means, so this means that all edges are of color 2. So if there is no, so either, so in graph Kn, either it have an edge of either it has an edge of color 2 or of color 1, or all edges have color 2, right? In which case so all edges color 2, it means that it has a clique on so this condition, all edges color 2, it's equivalent that it has a clique it has a clique on n vertices, so all vertices of the graph, n is the number of vertices in the graph. So on n vertices of color 2. So this statement basically means that we found, so it has either a clique of size 2 of color 1 or a clique of size n of color 2. So this condition is equivalent to it has a clique. Okay, let's write it here. So this condition, it has a clique on 2 vertices of color 1. So either it has a clique on 2 vertices of color 1 or it has a clique on n vertices of color 2. So this means that R of 2n is less or equal than n. Right? So because we took a complete graph on n vertices and we proved that it has either a clique of size 2 of color 1 or a clique of size n of color 2. So that's basically what it means. So by symmetry, we similarly have the inequality that R of n2 is also less than n just by replacing the color 1 and color 2. So this also holds. So this is the base of induction, and then we take the inductive step. So for inductive step, we are going to prove that R of xy is less or equal than R of x minus 1 y plus R of x y minus 1. So if we prove that, that would be the step of induction, because we conduct induction on x plus y. So so to prove this, we consider, so take a graph on this number of vertices. So now we have, so we fix x and y, and we take a graph on this number of vertices. So we consider a complete graph on R x minus 1 y plus R x y minus 1. And we are going to prove that this graph has either a clique of size x of color 1 or a clique of size y of color 2. So this would prove this inequality. So we take this complete graph on this number of vertices, and we consider, we pick any vertex, basically. pick any vertex, call it V. So now the remaining of the graph we divide it into two sets. So let's say set A and set B by the color of edges that connected to V. So all the edges from V that go from V, they have either color 1 or have color 2. There is no other possibility. So all edges are colored in two colors, right? So the edges from V, they're colored, some of them are colored in color 1, some of them are colored in color 2. Like, and V, so all the vertices that like the other end of these edges of color 1, we call it set A, and the remaining that connect to V by an edge of color 2, we call it set B. So yeah, so no, like it can be that one of them is empty. So like we doesn't assume that both of them are non-empty. So it could be that either A or B is empty. So, but what we can conclude is that the size of either of them, like they can be both small, because the sum of the sizes of A and B, like in total we have this number of vertices in the graph. So so let's write this carefully. So the size of A, the number of vertices in A, plus the size of B plus 1 is exactly equal to this, to the number of vertices in the whole graph. So R of x minus 1 y plus R of x y minus 1. So therefore we can conclude that either either the size of A is less or equal than this, is less or equal than no, not less, but greater or equal. Yeah, greater or equal than R of x minus 1 y, or the size of B is greater or equal than R of x y minus 1. So why is that? So this is just by contradiction. So because if both of this is not true, so if both this is not, if both this is not true and this is not true, so like in brackets we write, if both not true, then what we have is basically the size of A is strictly less, so the size of A is strictly less than R of x minus 1, x minus 1, y. And the size of b is strictly less than r of x, y minus 1, right? And then we write that that the size of a plus b is strictly less than the sum r of x minus 1 y plus r of x y minus 1. Now the size of a plus b is actually equal to this sum, so sum of a plus b plus 1 is equal, so therefore we can write that this is equal to, so this sum is equal to the size of a plus b plus 1. So let's rewrite this. So this is equal to the size of a plus b plus 1. Yeah, well, yeah, we can slightly improve this, so we don't obtain a contradiction here, but we write, so there is an additional step. So if, because both of these are natural numbers, so the strict equality implies that we can write that this is, we can write that the size of a is less or equal than r of x minus 1 y minus 1, right? So if natural number is strictly less than this natural number, then it is less or equal than this number minus 1. And similarly, the size of b is less or equal than r of x, y minus 1 minus 1, like this, from this inequality. So, and now from this we conclude that the sum of a plus b, yeah, so let's adjust this. The size of a plus b is less or equal than is less or equal than minus 1 plus r of x, y minus 1 minus 1. This is equal to r of x minus 1 y plus r of x, y minus 1, like this, minus 2. So this minus 1, this minus 1, and this is equal to so this sum is exactly equal to a, the size of a plus the size of b plus 1. So minus 2. This minus 2 we rewrite it as this. So this equal to the size of a plus the size of b minus 1. Okay, so now we look at where we started. So the chain of inequalities was well, first inequality and inequalities. So the size of a plus b, we concluded that it's less or equal than the size of a plus b minus 1, right? So a plus b is less or equal than a plus b minus 1. So this is a contradiction. This is a contradiction. Now I close the brackets. These are large brackets. So this is where I started with the brackets, right? So this was to prove that either the statement that either we have this inequality or this inequality, because if both of them are not true, if size of A is less or equal and size of B is less or equal, then by this chain of inequalities we obtain a contradiction. So either one of this is true. So then what we conclude is that, so if the first case holds, so if this inequality holds, then we can take a complete, like a clique subgraph that is a complete graph in A of size either of color 1 of size x minus 1 or of color 2 of size y. So okay, so let's write this below. So let's again draw our picture. So we have the set A, the set B, our vertex V, all edges to set A are color 1, all edges from V to set B are color 2. So we have two possibilities, right? So the first possibility, so option 1, so option 1 is that, let's call it case 1. Case 1 is when the size of A is greater or equal than R of x minus 1 y. So the case B will be when the size of B is greater or equal than R of x, y minus 1. But so in this case, so then by the definition of this number R of x minus 1 y, so there exists either a clique on x minus 1 vertices of color 1 in A, clique in A, clique in A, or a clique in A on Y vertices of color 2. So again, there are two possibilities, so we consider separately these two subcases. So this is subcase, so let's write it case 1.1, because this is within case 1, so this case 1.1 is when we have a clique, when we have this basically. When we have a clique, there exists a clique vertices of color 1. Clique in A. So if there is a clique of x minus 1 vertices in A, so somewhere here on x minus 1 vertex, so we just add vertex v, and this would be a clique on x vertices in the original graph. So then we add v to this clique, and this would be this would be a clique on x vertices of color 1 in the original graph G. Or we didn't denote it by G, but like in the original graph. In the original graph. In the original graph. And so basically this proves this case. So that's what we needed to prove. One of the options that we needed to prove. So now the second case is even easier. So the case, not the second, but case 1, 2. So case 1, 2, when there exists a clique in A on y vertices of color 2, but this, like the same clique is in the original graph, and on y vertices of color 2, this is the second option that we needed to prove this. So this already concludes the proof. So we take it as a clique in the original graph. In the original graph. Yeah, so both of these subcases, 1, 1 and 1, 2. So in both of them we found a clique that we needed to find. Yeah, so now case 2 is symmetrical. So case 2 so case 1 was when A is greater or equal than this. So case 2 is when size of B is greater or equal than R of x, y minus 1. Yeah, so this is symmetrical. Symmetrical to case 1. So just to briefly repeat the argument on the picture. So for case 2, right? So when we have the size of B is greater or equal than R of x, y minus 1, then by the definition of R, so B is greater or equal than R of x, y minus 1. So by the definition of this, we must have either a clique of size x, of color 1 in B, or a clique of size y minus 1 of color 2. So in first subcase, when we have a clique of size x of color 1, this is the clique in the original graph of size x of color 1. So this is what we needed. But in the second case, this is of color 2, clique of color 2 of size y minus 1. So it's one less vertex than we need, but we just add vertex v, because all edges from v to all vertices in the set B, they have color 2. So we add vertex B, and this clique of size y, now is one more vertex, has color 2, and this is the clique that we needed. So the two subcases are considered symmetrically to case 1. Yeah, so this concludes the step of induction and the whole proof. That's it.